All right, hello, this is a video for section 4.2 of the OpenStax Calculus 1 textbook. So this section is on linear approximations and differentials. We're going to restrict our video to just the linear approximations. So let me read this paragraph here just so we can kind of get the idea of what we're doing. It says, we have just seen how derivatives allow us to compare related quantities that are changing over time. In this section, we examine another application of derivatives, the ability to approximate functions locally by linear functions. Linear functions are the easiest functions with which to work, so they provide a useful tool for approximating function values. Okay, so we're going to be approximating function values using linear functions. Okay, it says, in addition, the ideas presented in this section are generalized later in the text when we study how to approximate functions by higher degree polynomials. And that's a topic for Calculus 2, so we won't really get into that. Okay, so let's go ahead and take a look at the idea. We'll just jump right into the problems, but essentially what we're doing here is we can take a look at a function like f of x equals 1 over x. This is, slightly more complex than a linear function. And so what we do is for this function 1 over x, which, looks like this, we draw the tangent line at some x value, and then we use this tangent line to approximate values of f of x using the linear function near x equals 2 in this case. Okay, so in the textbook, they kind of zoom in on this little boxed section there where x is equal to 2. And if you zoom in on that section, you can see that the line, which is in blue, is approximately equal to, they almost look the same. They almost look like they're both linear functions, but we know that the red graph is the function 1 over x. And so if we wanted to approximate, let's say we wanted to find f of 2.1, then that is equal to 1 over 2.1. But I don't know what that's equal to. And so if I find the tangent line, which is given here, we can just evaluate this function. This is usually called L of x, the linear approximation of f of x. So we can just find L of 2.1, and this is approximately equal to f of 2.1. And L of 2.1 is a lot easier to compute. Once we find the linearization, the equation, it looks like it came out to 1/2 minus 1/4 of x minus 2. And so L of 2.1 is going to be 1/2 minus 1/4 of 2.1 minus 2. And this computation here would be a lot easier than doing this division, especially if you had to do a lot of approximations near x equals 2. The linear function would accomplish this in a much easier fashion. Okay, and I won't compute it. We'll do some examples in just a moment. But you could figure this out. 1/2 minus 1/4 of 2.1 minus 2, that's 0.1 or 1/10. Then you multiply the fractions, subtract, and then you've got your approximation. Okay, so let's take a look. Actually, they actually even do this right here. The linear approximated value is, this ends up coming out to 0.475, it looks like. It says it right here. And the actual value, if you were to use a calculator to compute this value or use long division, the actual value is 0.47619. And so you can see that the y values of these points are very close to one another. And so the linear approximation works as a reasonable estimate for the actual function value. Okay, so let's go ahead and take a look at an example. We'll just do the one that's here in the text. Let's write down the definition here for the tangent line approximation, or sometimes called the linear approximation or linearization of f at x equals a. It goes by a few different names. It is this here. L of x, let me write it on the next portion. L of x is equal to f of a plus f prime of a times x minus a. Okay, and that's just the point slope form for the equation of a line, right? You've probably seen it as y equals y1 plus m times x minus x1. Here, we just let x equal a, so y becomes, oops, let x1 equal a, so y1, which is just f of x1, becomes f of a. And we know that the slope that we're referring to is the slope of the tangent line, which we learned here in calculus, that this is just the derivative evaluated at a. Okay, so that's how this equation becomes what we call the linearization of f at x equals a. All right, so let's go ahead and take a look at this problem here. It's a very nice problem. It can help, the linearization can help us to approximate square roots. So here we're given a function, given f of x equals the square root of x at x equals 9. And let me use as at a equals 9 just to kind of follow the notation. It says use the approximation to estimate the square root of 9.1. Okay, so I'm sure if I ask anybody listening to this, what's the square root of 9? You could tell me pretty easily. But if I ask you what the square root of 9.1 is, that's a little bit more difficult. And so we can use the linearization to answer this question. Okay, so excuse me. Here, a is equal to 9. And so I'm going to find, let's start with f of a, which is f of 9. This is the square root of 9. And that's easy. That's just 3. Now we can find f prime of a. Let me highlight it with a different color. Well, for that, we first have to find f prime of x. So f of x can be written as x to the 1/2. So f prime of x is equal to, using the power rule, we bring down the power, 1/2 x raised to the negative 1/2. And that negative exponent we know means that this is times 1 over x to the positive 1/2. And going back to the square root form and multiplying the two fractions together, we get 1 over the square root of 1 over 2 square root of x. Okay, so there's f prime of x. We want f prime of a, and a here is equal to 9. So f prime of 9 is equal to 1 over 2 square root of 9. What is this equal to? This is equal to 1 over 2 times 3, or 1 over 6. All right, and so now we're ready to write down our function. We know a is equal to 9, so we're ready to write down L of x. So the linearization, I'll write it in words here, linearization of f of x equals the square root of x at, let's say, a equals 9 is L of x, which is equal to f of a, 3, plus f prime of a, 1/6, times x minus a, 9. Okay. And so the function, the square root of x, is approximately equal to, so this is a decent approximation of f of x, near the value a equals 9, near x equals 9. Okay, so you could say that these two are almost the same function. They're clearly not the same. One is a square root radical function, and the other one is a linear function. But as you can see from the picture, when you zoom in a lot, you can't really even tell the two functions apart. They look like they're the same. That's the whole point of this linearization. The tangent line approximates the function really well near the point of tangency. Okay, so uh, good. Let's go ahead and now approximate the square root of 9.1. So here I'll use, let me do both here. The f of 9.1. This is the actual value. This is going to be the square root of 9.1. I'll use a calculator in just a moment to figure out what that is. And this is approximately equal to L of 9.1. Now I'm going to use the linearization at x equals 9.1 to approximate the value. So this is equal to 3 plus 1/6 times 9.1 minus 9. And so this is 3 plus 1/6 times 0.1. And so let's walk through this here. The 0.1 is going to be, we know that that's 1 in the tenths place, so 1/10. And so we can multiply those fractions to get 1 over 60. And if we, excuse me, if we get a common denominator of 60, then we end up with 180 over 60. And so this is equal to 181 over 60. So this fraction here approximates the value of the square root of 9.1. Now we could kind of further simplify this. This is 180 plus 1 over 60. We know that 180 is divisible by 60. Yeah, maybe I should have, let's see, I was trying to find a way to find this number in a nice way, but 1/60th, what is that equal to? Well, maybe we should revert back to here. 1/6, you may know that what that's equal to. 1/6 is approximately equal to 0.16666 repeating. Okay, so 1/10 of that, when we multiply by 1/10, we know the rule, 1/6 times 1/10. That just moves the decimal place over one place to the left. And so that would be 0.0166666 repeating. Okay, so this is approximately 0.01. And we'll go to, yeah, let's do 1, 2, and we'll round to 7. And so if we add these two numbers together, we get approximately 3.01667 as our approximated value. Okay. What's the exact value? The square root of 9.1. Let me get my calculator. The square root of 9.1 is, and here I'm going to use quite a few decimal places. Let me approximate it actually. We'll do 3.01662. I'll stop there just to show that, you can see there is a difference in these two values. They're not the same, but the difference is not until the, let's see, tens, hundreds, thousands, 10,000s, 100,000s. So they differ by a very, very small amount. They're practically the same number. Okay, so this is what we would call the actual value. Excuse me. Okay, so notice that when I did this here, I didn't have to use my calculator to find the approximation. Whereas this, we might have a tougher time computing. The linear function in general is better or is uh, easier to compute values with than the, nonlinear function, like the square root function or the log function or the tangent function. Um, so, this is a useful tool for us. All right. Just very quickly here, let's highlight some of the similarities in the solutions. So we had our linearization, which was here in the textbook. Yeah, essentially they found the same thing. And then what did they do? They just plugged in 9.1 into that linearization and got approximately 3.0167, which is, essentially what we got. They just rounded to a different number of decimal places. And they computed, also using a calculator to 3.0166, which is very close. All right, so let me read this paragraph here just to summarize. It says, using a calculator, the value of the square root of 9.1 to 4 decimal places is 3.0166. The value given by the linear approximation is 3.0167, is very close to the value obtained with the calculator. So it appears that using this linear approximation is a good way to estimate the square root of x, at least for x values near 9. At the same time, it may seem odd to use a linear approximation when we could just push a few buttons on a calculator to evaluate the square root of 9.1. However, how does the calculator evaluate the square root of 9.1? The calculator uses an approximation. In fact, calculators and computers use approximations all the time to evaluate mathematical expressions. They just use higher degree approximations. Okay, so kind of a little bit of a dive into, how does the calculator know what the square root of 9.1 is? It uses an approximation itself. Now, one thing I also want to point out here, it says the linear approximation is a good way to estimate the square root of x, at least for x near 9. Yeah, because if you notice that if you choose x values that are not near 9, like let's say x equals 0, this linear approximation will not be very good because the linear approximation that we computed was for the x value or a value at 9. So the two functions will be very close to each other near 9, but away from 9, you would have to compute a different tangent line. You could also compute the tangent line at x equals 0 or at x equals 1 or a different value to get if you wanted to approximate values near a value other than 9. Okay. So if we wanted to find the square root of 9.2, we could use this same linear approximation. All right, so very good. There's a problem here you can try yourself. It says to find an approximation to the cube root of 8.1. Now we're getting to this would be even tougher without a calculator, tougher than the square root. But with linear approximations, it can be done pretty easily, just as easy as, excuse me, the problem that we just did. Okay, so let's go ahead and give another problem to try. Let's try another example. It says, find the linear approximation of f of x. So let's go to a new page. F of x equals sine x at x equals pi over 3. Okay, and use it to approximate the sine of 62 degrees. Okay. All right. So let's go ahead and let me write down the formula here for the linearization. L of x. This is going to be f of a plus f prime of a times x minus a. And so here our value that we're interested in approximating near is pi over 3, which is, 60 degrees. I'll just write that down here. Usually we use radians when we're doing calculus with trigonometric functions, but it's, 60 degrees. So we can use it to approximate the sine of an angle near 60 degrees, like 62 degrees. Okay, so let's go ahead and find the linear approximation. So L of x is going to be f of pi over 3 plus f prime of pi over 3 times x minus pi over 3. Okay. Yeah, and hopefully before we get too far into this problem, ask yourself, how would you compute the sine of 62 degrees? That would be quite difficult. Think about that for, a minute. Well, we can use the tangent line for the sine function near x equals pi over 3, and it'll be relatively easy that way. So let's go ahead and find f of pi over 3. That the function f is just a sine function, so the sine of pi over 3. Let's see, pi over 3 is 60 degrees. If we remember our trigonometry, this is root 3. This is pi over 6. So this would be 1, and this would be 2. And so sine is opposite over hypotenuse. Okay, good. Root 3 over 2. F prime of, let's figure out what f prime of x is. The derivative of f, the derivative of sine, we know is cosine. Okay, so cosine of x. And we want f prime of pi over 3. So f prime of pi over 3 is cosine of pi over 3, which is adjacent over hypotenuse. That is 1/2. All right, so now we're ready to go back to our linearization. L of x is f of a root 3 over 2 plus f prime of 3, which is 1/2, times x minus a pi over 3. Okay. So this line is approximately equal to the sine function. So I will put approximately equal to the function f of x, which is sine of x. So, excuse me, if we want to find the sine of 62 degrees, we just plug in 62 degrees. But as I mentioned, we should plug it in terms of radians. So 62 degrees in radians, we multiply by 180, or pi over 180. And so this is 62 pi over 180. And so sine of 62 degrees is equal to the sine of 62 pi over 180 radians, which is approximately equal to L of 62 pi over 180, which is root 3 over 2 times 1/2, plus 1/2 times, let me plug in my angle here, 62 pi over 180, minus, let's go ahead and get a common denominator here. We'll multiply by 60 to get a denominator of 180. So this is going to be 60 pi over 180 equals root 3 over 2 plus 1/2 of, this is 2 pi over 180. These 2's are going to cancel. And so we have root 3 over 2 plus pi over 180. All right, and then let's go ahead and take a look here. Yeah, at this point in our solution, we could compute this. I'm not going to take the time to compute this also without a calculator, um, but we definitely could, because in the previous example, we showed that we can calculate square roots um, using linear approximations. Uh, Pi, we can calculate to quite a few decimal places if we have that memorized. Um, and then, so we can compute this value here, and we get approximately 0.88348. So let me write that down. This is approximately equal to 0.88348. And let's see, what is the sign of, let me use a different color, the sign of 62 pi over 180. I'm getting here that this is equal to 0.88294, and so on. So yeah, where do we differ? We differ here in the after the 0.88, but it's still relatively close. So the approximation is okay. Um, we can see again, we really want to understand the idea here. And the idea is that um, the tangent line, the line in blue, when you zoom in really close to the point of tangency, you can almost not tell that red curve and the blue line apart, right? They're basically the same in a sense. Okay, now we can see far away from the point of tangency, they differ by quite a lot. So the further that you go away, if I want to find the sine of 2 pi, uh, or the sine of, let's say, pi, which we know is equal to 0, well, this tangent line is not going to be a good approximation uh, at pi, or 180 degrees, because our approximation is centered at 60 degrees. All right. That is, um, you know, a good summary of linear approximations. There is one more problem. I, challenge you to try it on your own, um, and then just check your answer here in the textbook. The textbook is available for free online on OpenStax.com. You just Google OpenStax Volume 1, and you can view it there. All right. Well, thanks for watching, and we will see you next time. Okay, now how do I turn this off? Mhm.